If you've ever looked at a car frame, a skyscraper, or even a massive ship, you've seen the work of a welder. And there's a really good chance that work was done using one of the most popular and versatile processes out there, gas metal arc welding. So today, let's break down the science, the skill, and the secrets behind the weld that literally holds our world together. So what makes GMAW the go-to choice for so many people? Well, it really just boils down to one thing. It is the industry's ultimate workhorse. It finds that perfect balance between speed, quality, and adaptability, which makes it just incredibly valuable for countless jobs. Okay, so here is the formal definition from the American Welding Society, but you've probably heard it called MIG welding, right? For metal inert gas, or maybe even just wire feed welding. Now, while MIG is still a super common name, the official term is GMAW. So why the difference? Well, MIG implies the gas is always inert, and that's just not the case. We're going to get into how using different gases can completely change the game in just a bit. And this image right here, it lays out the core setup perfectly. You can see the power source, you see the wire feeder, and that all-important cylinder of shielding gas, all of it feeding right into the welding gun. And trust me, it's a setup you will find absolutely everywhere, from huge industrial factories to small fab shops, joining everything from thin sheet metal to thick, heavy-duty structural steel. To really, truly master GMAW, you have to understand the three fundamental pieces that come together to create the weld. Everything, and I mean everything, comes down to this delicate dance between the wire, the gas, and the arc. Let's break it down into what I like to call the three pillars. So first up, you've got the consumable electrode. That's the spool of wire that's always feeding through the gun. It does two jobs. It carries the electrical current, and it melts to become the filler that joins the metal together. Second, the shielding gas. This creates a protective bubble, like an invisible force field right around the weld. And third, you have the electric arc itself. That's the superheated plasma that provides all the energy to melt everything together. All the magic happens right where these three things meet. Seriously, think of that shielding gas as an invisible force field. Its job is absolutely critical. Without it, the molten metal would instantly react with all the oxygen and nitrogen in the air, and you'd end up with a weak, porous, brittle weld just riddled with defects. This gas shield is probably the single most important element for creating a strong, solid connection. And this brings us right back to why calling it MIG can be a little misleading. The shielding gases really fall into two main camps. On one side, you've got inert gases, like argon and helium. They don't react with a weld pool at all. This makes them perfect for sensitive, non-ferrous metals like aluminum. But on the other side, you've got reactive gases, most commonly carbon dioxide, or maybe a mix of argon and CO2. These gases actually take part in the weld chemistry, which for steels can mean you get much deeper penetration, though sometimes, it comes at the cost of a little more spatter. Now, here is where it gets really interesting. Picking a gas and setting your machine doesn't just protect the weld, it fundamentally changes the physics of how the molten metal actually gets from the wire tip to the workpiece. We call this the mode of metal transfer. And you can see that difference in action right here. Look on the left. Gases with a lot of argon can give you a very stable, focused arc. Now look all the way to the right. Pure carbon dioxide creates a much more forceful and sometimes less stable arc. And this isn't just some textbook detail. This directly impacts the kind of weld you can physically produce. So this gives us four basic modes. At low energy, you get what's called short-circuiting. The wire literally taps the weld pool, shorts out, and deposits a small drop. It's a cool and controlled process, which is perfect for thin material. Next up is globular transfer. This uses higher energy with CO2, and it basically lobs these big, irregular drops across the arc. It's fast, but it can get messy. Then there's spray transfer. With a high argon gas mix, you get this smooth, clean stream of tiny droplets, perfect for high-speed welds on thicker stuff. And finally, you have pulsed spray, which kind of gives you the best of all worlds. Pulsed spray is a much more advanced, digitally controlled process. What the machine does is it rapidly pulses the current between a high peak and a low background level. This allows it to detach one single, perfectly formed droplet for every pulse. It gives the welder incredible control over heat input and bead appearance for pretty much any application you can think of. So, okay, we understand the process. But how does a welder actually make the right choices before they even strike an arc? Well, it all starts with the spool of wire itself, which is usually covered in what looks like some kind of secret code. You might see something just like this on the side of a wire spool. So what on earth does E70C6M actually tell you? All right, let's decode it. E is easy. It just means electrode. The 70 is the important one. It tells you the finished weld has a minimum tensile strength of 70,000 pounds per square inch. To put that in perspective, that's like hanging 3 full-size cars from a single 1-inch square bar of this weld metal. C means it's a composite or metal cord wire. The 6 defines its operating characteristics, and finally, that M tells you it's designed to be used with a mixed shielding gas. See, all of a sudden, the code makes perfect sense. So, here's the crucial point. Choosing the right wire is so much more than just decoding a label. A welder has to think about what they're welding, how strong it needs to be, and whether they're welding flat on a bench or, upside down under a bridge. Each one of these factors is a piece of the puzzle, and a skilled welder has to consider all of them to pick the absolute perfect filler metal for that specific job. Okay, so we've got the right wire, we've got the right gas. Now comes the real skill, bringing it all together and dialing in the machine to lay down a perfect weld. A welder is constantly juggling all of these key variables. The wire feed speed, that controls the amperage, which is basically the heat. The voltage controls how long the arc is. Then you have how fast you move the gun, the angle you hold it at, how much wire is sticking out. It's a constant balancing act. If you change just one of those variables, you almost always have to adjust another one to keep that arc stable and doing its job. And hey, it's not just me saying this. This quote from the Welding Handbook makes it crystal clear. This is not guesswork. It's a science. The ability to understand and precisely control these variables is what separates an amateur from a professional. It's what ensures every single weld is just as strong and reliable as the one before it. And I mean, the results really speak for themselves. On the left, you can see what happens when those variables are out of balance. You get an inconsistent, defective weld that's just not structurally sound. But on the right, with everything dialed in perfectly, you get a beautiful, uniform, strong, and satisfactory weld. The difference between failure and success really just comes down to control. So, at the end of the day, when you look at GMAW, you're not just seeing a tool. You're really seeing a complete system. It's this amazing intersection of electrical engineering, material science, and fluid dynamics, all harnessed by the steady hand and deep knowledge of a skilled operator. They're not just joining metal. They are creating bonds that are engineered to last a lifetime. So after seeing all this complex interplay of chemistry and physics and hands-on control, what do you think? Is welding ultimately an art form, or is it a masterful application of science?